All right. I'm going to hand this attendance sheet around again, since there are newcomers. Yeah. And it's actually start a class now. Oh, the code? Oh, I'm sorry. I know. There. Now your life will be complete. I offered another class a chance to guess the top hat code for 20 bonus points. But after he made the guess, I warned him that if he guessed wrong, he lost 10. But I only announced that after he made his guess. But I'm not enforcing it.
Did he get 20 or
probably. What's that?
Did he get 20
No, he did not get the 1 in 10,000 chance that he. No. All right. So I'll begin with a word of prayer. Dearly Father, we thank you for this day. I thank you again for these students. Just ask that you just bless our work today. Help us to glorify you, what we do, Lord. In your name I pray, Lord Jesus. Amen. So today I need to talk to you guys about the concept of a tangent space. And so what is tangent space? Really, for us, for the most part, just the tangent plane. Although, I mean, to be honest, we've already talked about the tangent space in the one-dimensional context, right? Because I talked to you guys about how to find the tangent line to a curve and parameterize it, right? And so that, the one-dimensional case is kind of boring in some sense, but for a curve, right? Let's think about it this way. Not a curve, a surface, rather. So we could have a surface. This could be f of x, y, z equals to some constant, let's say c, all right? So, for instance, we can run with this example here while we're doing it. X squared plus y squared plus z squared equals to, we could let the constant be r squared so it has more meaning. That's a what? That's a sphere, right? So, but generically speaking, if you have some equation of x, y, and z, you set it equal to a constant, there's some solution set, right? And that solution set is a surface in 3 dimensions, right? So here it's a sphere. Of course, you could make cones. You could make. We've studied planes, right? And so if you pick a point in the surface, like this point P, right? Then we can think about curves going through that surface, right? Like this. And what would it mean if this point right here is, parameterized by gamma of t? What would it mean? What equation would we have for the curve that goes through the surface? Well, we'd have f of gamma of t, right? Equals to what? Well, it would equal to c if it's on this surface, right? And then what could we do? Well, we could differentiate this, right? We could differentiate this, and we could use the chain rule. So the derivative of f of gamma, it's supposed to be gamma, f of gamma of t would be chain rule gradient of f evaluated at the curve, right? Dotted with the velocity d gamma dt, right? And that has to be equal to 0 because the derivative of the constant is 0, right? So what does this reveal about the tangent vector to the curve? So let me kind of picture this thing on the curve. It's something like this, right? My gammas keep deconstructing. They're not structurally integral. So if I, let's suppose that P is gamma of 0 just for the sake of specificity here, right? So this is actually d gamma dt of 0, right? In that case, that would be the tangent vector to the curve at the point. And what do we see here? We see that the gradient of f, right, at the point P dotted with the velocity is equal to 0. So this is setting t equals to 0. We get this, right? What does it say? Well, this says that the gradient vector has to be perpendicular to the velocity vector of a curve that lies in this surface, right? And can you do this? You could do this for a bunch of curves, right? You don't have to do it for just one curve. You could keep doing this, right? I could also do it for like this curve, right? And that would give me a different velocity vector, right? Like this. And I can keep repeating this process, right? And if you think about it, we're going to like fill out a plane from all of those vectors pasted together, provided that the surface is what's called, differentiable at that point. If there actually is a tangent plane, the tangent plane should be filled out by the collection of all these vectors to all these curves. Does that make sense? At least in principle? Now, what's the normal vector to that plane? What's the normal vector to my tangent plane? Yeah, it's this exactly is going to serve as the normal to the tangent plane. So if I want to figure out what's the tangent plane, so I've got this sphere, right? I pick a particular point. Let's say x naught, y naught, z naught. I mean, why not, right? That point. What's the equation to the tangent plane right there for this sphere? So all we do, very simple, calculate the gradient of the level surface. I should probably write it here. I'm going to run out of space. Gradient of f. And I have to plug in my point, which in this case is p, right? So I'm going to do what? I'm going to get, fine, I'll write gradient of f up here symbolically. It's what? It's 2x, 2y, 2z. You're like, why didn't you put that one on the quiz? I'll get there. And then we plug in the point, right? And we get what? We get 2x naught, 2y naught, 2z naught, yeah? So what's the equation of the tangent plane then? That's its normal, right? What's a point on the tangent plane? Well, this point, x naught, y naught, z naught, right? So the equation of the tangent plane would just be 2x naught times x minus x naught plus 2y naught times y minus y naught plus 2z naught times z minus z naught equals to 0. There you go. That is the equation of the green tangent plane right there. All right. Now, of course, you could put in numbers, right? I mean, if we had, I think numbers actually clutter it here. It's better to just kind of leave it more symbolic for the first example. Let's do another. And this example is again going to be an example of example. Well, this is an arbitrary point on the sphere, right? The formula is pretty nice here in that regard. But example 2 is just going to be, suppose we've got z equals to f of xy, all right? Let's find tangent plane at a comma b comma f of ab. All right? And I'm assuming here that the function that we're looking at of two variables is like, differentiable and such. I think Math 200 is much worse than this course. Come on, isn't it? Isn't Math 200 worse than this course? You're Math 200, no?
Worse than this course?
Yeah, worse than this course. Yeah, right. So, it could be worse, right? No? I don't know. Like, people ask me Math 200 questions, and I'm like, my brain. Negate this sentence. Like, I don't care about this sentence. I can't negate things I don't care about. I did teach that course a while ago, but anyway. By now I've forgotten all my contrapositives and yada, yada, yada.
Yeah.
So, But I know the contrapositive when it's math that matters to me. Like, I can do it logically. Anyway, it's good I'm not teaching that course. Maybe it's not. Maybe I'd learn that stuff better if I taught it again. It's been about 10 years. No, wait a minute. Oh, goodness. It's been 14 years. Man, I'm old. Let's see here. So find the tangent plane at that point, all right? So let us convert this to a level surface so we can just use the method we already developed. How do you convert this to a level surface? How do you make a graph a level surface? F of x, y, z equals to what? Can I make this, any graph I can make into a level surface if I want? How do I do it? How about this? You guys tell me. What do you want? I'm not going to, you guys never. I'm impatient. You just do z minus f of xy. And you want that to be equal to what? Equal to 0, right? If you do that, then the solution set to that equation is exactly the graph, right? So the difference between a level surface and a graph is really not so much. That's not true. Can you make the sphere a graph? A graph has to pass the vertical line test, right? Because it's z is equal to f of xy for each x and y, right? But the sphere, if I pierce it like this, right? I got this point and that point, let's say. They're both with the same x, y, and yet different z's, right? So I could graph the upper half of the sphere as a graph, or the lower half of the sphere as a graph, but not the whole thing. But it is a level surface nonetheless. So the concept of a level surface is more general than the concept of a graph. Quite a bit more. Okay, so anyway, what's the gradient here? And you notice that here we're thinking three-dimensionally, right? So nabla f would be gradient of f. I've got, fx, fy, fz, which here works out to what? Well, let's just write it this way. Minus fx, minus fy, and 1. All right? So if I take my gradient vector and I evaluate at the point of interest, which in this case is a, b, f of ab, what do I get? I get minus fx of ab, minus fy of ab, and, well, the last one's kind of not a very exciting evaluation, but it's still 1. There's my normal vector. So what's the equation to the tangent plane, to the graph? Simply the following, right? I do minus fx of a comma b times what? Minus fy of a comma b times what? Plus what equals to 0? There's a 1 here if you want to see it. So you guys fill in the blanks for me. What did I put there? By the way, the appointment thing I mentioned in the announcement, like if you're like 3 of you who have questions, you can like reserve 3 spots in succession, and I'll come to each other's spots and like be there at the same time. Like I'm not saying there has to be 1 person at one time, or that each person can only be there for 20 or 30 minutes. The point is each person can reserve a 20-minute, 30 spot. So like if there's 3 in your group, then you can reserve an hour. This needs to happen because it needs to happen this semester. I never do this, but it needs to happen this semester because I'm currently having some issues in office hours getting time for talking to you guys without frustrating the college algebra students. So, but anyway, so just a thought, if you do have questions, like and you can write your name up there, and if you don't come, it's like not the end of the world, but you guys know where my office is? So, if you think of it Monday morning, just go write your name somewhere. I'll shut up. Anyway, so what do I put in here? This is the A, B, C of the plane that we're writing the equation of. X minus A, right? Y minus B, Z minus C, no, Z minus f of AB. right? Now let's write this equation over again. See, because the tangent plane to a graph is itself a graph. Check this out. So we have z equals to what? Solve for z. What do you got? Z equals to f of AB, right? Plus fx of a comma b times x minus a plus fy of a comma b times y minus b. That right there, guys, is the equation of the tangent plane to a graph. Stuart probably takes this as a definition. We can take this as the definition. This is the equation of the tangent plane to z equals to f of x comma y at a comma b comma f of ab. All right? So if you have a graph, you don't necessarily want to go through this whole rigmarole I just went through, right? Maybe you just want to use what I just boxed as your go-to formula for how to find the equation of the tangent plane, right? Like, let me make it a little bit more concrete here. If I had, you know, z equals to f of x comma y equals to, say, x plus y over x squared plus y squared, that's kind of hideous, isn't it? A little bit. Let's find the equation to the tangent plane somewhere. And you guys give me a point. Let's see, find equation to tangent plane at, let's make it interesting, 1 comma 2, what's the z then? I'm happy no CFA has come today, right? Okay, I think I know you guys. In a class of 40, CFA might slip in, you know? Could happen. But I don't feel my strength being drained. So I feel like there's no CFA here. Actually, as demotivating the presence of a CFA is, I mean, they're not really that demotivating. The thing that's worse, the thing that's the worst, is like a parent visiting your class. That's just, it's just a game changer. I don't know. You worry because, like, you know, parents are very judgmental. You're like, am I doing something wrong? Like, you know, I don't know. It's very intimidating, personally. But 1, 2. So I plug in 1 and 2. I get 1 plus 2 is 3, and then I divide by what? I think 5, right? 3/5. Do you guys agree? Okay, so what's the tangent plane? Let me calculate fx. What is fx? It is, well, 1 times x squared plus y squared minus parentheses x plus y times 2x divided by x squared plus y squared squared. All right, so fx is actually equal to, looks like a y squared minus 2xy minus x squared divided by x squared plus y squared squared. Here's a fun trick to have in your arsenal. If the formula is symmetric with respect to x and y, right? You don't need to differentiate again. You just need to exploit the symmetry of x and y. So x and y's roles being reversed, what's fy equal to? I'll do the easy part. X squared plus y squared squared. What goes up top? Switching the roles of x and y. I'll do the... X squared minus 2xy minus y squared. Now, if you had been devoted to what I said more completely, you would have told me yx, right? But in your heart, you know that commutes, so you're like, come on, man, right? Very presidential comment. that you did not make. But anyway, you can think about it being made. Now, we have to evaluate these things, right? fx at 1, 2. Oh, man. But the good news is, I think once we, well, no, that's not quite true. The symmetry is spoiled. I can't assume that they're equal. But you guys plug it in, what do you get? fx at 1, 2 is 4 minus 1 over x squared plus y squared was 5, right? So 25. So it looks like minus 1 over 25 if I did my math right. You guys double check me on that. Fy of 1, 2, I believe I would get a 1 minus 4 minus 4, I guess, divided by 25, which would have been equal to minus 7 over 25. Do you agree or disagree, guys? You guys get minus 7/25. Okay, so what's the equation of the tangent plane? Equation of the tangent plane, here it is. Z is equal to the 3/5 we found earlier, minus 1/25 times x minus 1, minus 7 over 25 times y minus 2. There you go. So I was trying in vain to get across the idea of the general derivative yesterday. And what I was trying to get across, and maybe I need to flip the script and like do this material first. Maybe that would be better actually for me. To do this first and then talk about the general derivative so you have more sense of what I'm talking about with when I talk about linearizations. These are linearizations. This is the linearization of z equals f of xy. Z equals f of xy is some kind of curved space generally. This is a plane. This is the plane which closely approximates the surface z equals f of xy, the graph, close to the point AB, comma f of AB. This right here is the equation of the plane, right, which is approximately equal to the curve z equals x plus y over x squared plus y squared near the point of tangency 1, 2. Right? So if for some reason all you did all day long was calculate the number of widgets produced if you put the number of was-its and come up with a made-up word here. Let's say x is the number of elves and y is the number of leprechauns, and this is a formula for the number of widgets that elves and leprechauns make in whoever's workshop you want to talk about. Where do elves and leprechauns both work? I guess it must be Satan. Not the real Satan. This is a Satan in some sort of fictional, made-up universe. So don't be bad. Don't feel bad. It's not a satanic example. Man, now I'm starting to really feel happy that there's not CFAWs here. But anyway, if you were doing that all day long, and it just so happened that all of your elves, you always had about 1 elf and 2 leprechauns, then this would be a very good approximation for the number of widgets that you made. If you had, just like 1.1 elves and like 2.2 leprechauns in your shop. I allow for fractional elves and leprechauns in this example. So these could be in units of thousands of elves and thousands of leprechauns. I'm not a monster. I'm not cutting them in half or anything. So it's just, all right. Do you guys understand how we find the tangent plane to a graph? It's pretty simple. You just calculate the x derivative, calculate the y derivative, formula, right? It's even easier for a level surface. You take the level surface, you calculate its gradient. That's the normal, right? What's the other viewpoint? Like, well, isn't 2 viewpoints enough? Well, no. There is another viewpoint, which is the parametric viewpoint, right? For surfaces, what is that? So we basically got, you can draw a picture like this, right? Here's, let's say, UV space, right? And then over here is my surface. And what goes on is over here in UV space, you've got some, domain of parameters, and it gets mapped over here. It gets curved and like laid and glued on to this particular subset of 3 dimensions, right? So you might have these horizontal lines, right? They get mapped to maybe something like this, all right? Right? And the blue lines are like vertical lines, all right? They're like this, maybe. And they would get mapped onto these curved lines over here, something like that. And I typically use a R or an X. What do you guys, tell you what, I'm going to use big X. It's easier to see. I'm going to use big X as the parameterization map, just so you can see it better. I sometimes use, I either tend to use either big X or R for my parameterization map, but I use R for a lot of things, right? So, okay, so what this does is you take a particular point here, right? That point would say be U naught, V naught, right? And that maps to like this point over here, let's say, and that point would be X of U naught, V naught. And that's going to be our point of tangency we're studying. All right, that's the point of tangency I want to describe. How do we find the equation for the tangent plane at that point from the parametric viewpoint? So I started to talk about this the other day in terms of the so-called partial velocities. But let me just try to be really explicit about that. So the one curve that goes like this, let's say, I'll make it green, is what it is this curve right here fed through the parametrization. Now that curve right there, what's the equation for it? The equation for that curve is exactly U equals to V naught. Excuse me, U naught, my bad. That's the equation of a vertical line in UV space, right? Like if instead of having U and V, you had X and Y, if I told you X equals to 2, you should know that that's a vertical line, right? So if I define, say, gamma of t, and I'll call it gamma sub, let's see here. I'll just call it gamma sub 1 because I don't want to make a decision. Gamma sub 1 of t would be like X of U naught, comma V. See, the green line, this parametrizes, and if I put a t here, what do I put here? I put a t there, but instead of using t, let me be more honest. The parameter of gamma 1 really is V. Okay, let's embrace the notation. So the V parameter, I take whatever V is here, and that gives me the point over here. So like, this parametrizes the green line. I should say green curve, it's a curve, right? And if you can do that, well then you can also, if I can find another color. Hey, I got purple. Haha. I can look at the other line, like this one here, right? What's the equation of this purple dude right here? Instead of U equals U naught, we've got what? We've got V equals to V naught, right? And so like gamma 2 would take U as its parameter, right? And the formula for that explicit would be X of, well, U comma V naught, right? So this parametrizes the purple curve. So I'm trying to describe the tangent plane to the parametrized surface, right? So if I can find two tangent vectors into the plane, you guys remember how this goes. To find the equation of the plane, how do you do? You find two tangent vectors, right? And once you do that, what do you do? You're like, oh no, he's going to talk about, yeah, that's right, the cross product. We're going to take the cross product. Now, how do we find the tangent vectors? Can you guys tell me? How would I find like this tangent vector and that tangent vector? Let me just call this one V1 and V2. Yeah, just exactly. V1, I could be, you said gamma 1 prime, right? Of what? And V2 would be like gamma 2 prime of what? I want to get this point right here, right? This point of tangency I'm trying to describe. So I should plug in V naught for gamma 1, and I should plug in U naught for gamma 2. But you guys tell me, what am I doing here if I differentiate this path? I'm doing what? I'm varying V while holding what? While holding the other independent variable U naught fixed. What is that? That is a partial derivative with respect to V. So this is exactly partial x, partial V at the point U naught V naught. And by the same logic, V2 is exactly partial x, partial U at the point U naught V naught. These are what I called the other day partial velocities, partial velocities of the parametrization. I may not even have that language in my notes, but I should. I think it's good to have a label for these things. They're the partial velocities. Because a parametrization, it's two-dimensional, right? So there's two different parameters to vary. And so two interesting things to look at and specifically are the partial velocities, like what happens when you fix one parameter and vary the other, or vice versa. So V1, and what's the normal? You've got V1 and V2, so the normal would be what? Normal vector, you do V1 cross V2, right? So let me put this all together. Here's the theorem. Partial x, partial u cross partial x, partial v equals to n of uv is a normal vector field to S, which is equal to, let's say, x of d, where d is a subset of R2, the so-called parameter space, and x is the mapping from d to S, which is a subset of R3. So I just added some terms and conditions to what we just did, but that's a summary of what I've just shown you. If we have a mapping from a subset of R2 called parameter space, the domain of the parameters, to R3, this basically pastes the parameter space in a curved sense up onto this surface. All right, in that case, if we take the cross product of the partial velocities, we actually get a normal vector field. What's a normal vector field to a surface? What do I even mean by that? I only have flat surfaces in here, so, well, I guess I'll use my head. That should be in camera. So, this would be a normal vector field to my head. Although it gets kind of, maybe that's not really a surface, I don't know. But anyway, you get the idea. So the normal vector field, if you could put a plane to the surface, the normal vector field, let me just draw a picture. So the normal vector field has to do what? It has to poke, like, I don't know if my picture is really doing it justice, but maybe you get the idea. I can't do very well there, but it's perpendicular to the surface, right? It would provide you the normal to the tangent plane at each point that you asked about. Provided the surface actually was a differentiable one that had a tangent plane. Can you guys tell me, in view of this formalism, when is there not going to be a tangent plane? U equals to v? Well, u equals to v is okay. I mean, we could still have that the partial velocities when u equals to v are different. But what if xu is equal to xv? Maybe that's what you mean, right? If these are equal, if the partial velocities are equal, you take the cross product, what do you get? You get 0, right? In fact, if the partial velocities are collinear, right? If they don't genuinely go in different directions, then you take the cross product, you get nothing, right? So a good surface, actually a reasonable parametrization for a surface must be one such that the cross product of the partial velocities is non-zero. So usually people say such a surface is a regular surface. A regular surface is one which has a non-vanishing normal vector field. And this parametrization, or sometimes people call it a patch. And the reason you call it a patch is because you were literally thinking about taking this flat patch and just patching the surface. If you could imagine this being like a ball and you were trying to cover it with a, like a piece of cloth with a, grid on it or something. It's a patch, right? This is a patch of the surface. So the patch to be, for the patch to be regular, you need that the cross product is non-zero. Otherwise, your normal vector field, well, 0, right? Now, you're like, well, could we talk about normal vector fields in the original viewpoint as well? What would you guys think? What would the normal vector field, what's the normal vector field to my first example in retrospect now? I mean, I can picture the normal vector field to example 1, right? Can you picture it? This one's easier. So going back to this one, the normal vector field, there's one of them, right? Like here, like here, like here, like here, 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 here. It's like the reason for the shutdowns, right? I mean, if you can remember those pictures of like the COVID molecule, kind of like that, like it's just all spiky, but completely symmetrical, right? So the normal vector field, the formula for the normal vector field is right here. That's the normal vector field. What is a vector field? Remember I said the other day a vector field is when we take an object and we attach a vector to each point in the object. So I'm talking about the normal vector field to a surface. In other words, we're attaching a vector at each point on the surface, and that happens to be a normal vector, right? The Frenet-Serre formulas, the Frenet-Serre discussion was all about putting a vector field along a curve. Each point of the curve we put a vector, right? Any questions? So you're like, well, example 1 seemed too easy. Let's do it parametrically, right? No? Yes? Should we start with something easier than that, maybe? I should probably save that for another day, because like the calculation of example 1 from a parametric perspective, it's a little bit tougher, because like what is the parametrization of a sphere? Spherical coordinates, yeah. That's true. So this one, we could do x of, let's say, phi theta equals to r cos theta sine phi, r sine theta sine phi, r cos phi. that indeed is a parametrization for the sphere. What would my parameter space be? D, I could let be 0 to pi crossed with 0 to 2 pi. This is the Cartesian product. If you want to know what that is, you can ask your friendly Math 200 students that are among you. But it's just pairs of things, right? So this is saying that the angle phi is ranging from 0 to pi and the angle theta is ranging from 0 to 2 pi. If you want to get the whole sphere, that gets the whole sphere. All right? So I'm not going to do this today, but a good exercise is to calculate partial x, partial phi, and take the cross product with partial x, partial theta, and see if you can simplify it. Because it actually does simplify pretty nicely. It has to. Because geometrically, this has to be equal to, up to, well, does it have to be equal to? You guys tell me this. Does this vector have to be equal to that vector? It doesn't have to be equal to it, but it should be plus or minus it, right? And up to a scalar multiple, because they're normal. So they should be collinear. I guess you might see an issue here, right? How do we choose a standard normal to a surface? If we want to like normalize this, normalize the normal, what should we do? How about this? We could make it length 1, right? If we made a unit normal field, then that would be like a length 1 thing, and that's what we'll do later. Okay, so example 4, I'm going to revisit the graph again. So graph z equals f of xy, right? I would like to point out to you that this we can just as well think of as a patch. It is a patch formed by what? What's my formula for x? Formula for x is x. Formula for y, y. Formula for z, f of xy, right? So this is, I'm looking at a graph as a parametrization. We can do this. Wait a minute, you said that the graph was a level surface. Now you're saying that a graph is a parameterization. That's right, the graph is kind of a middle ground. Because in the graph, you're using the Cartesian coordinates as the parameters. This is where the worlds collide. The viewpoints are comparable. Now, and so if we calculate the partial velocities here, partial x, what do we get? We get 1, 0, fx, yeah? And if we calculate partial x, partial y, what do we get? We get 0, 1, fy, right? And so if we calculate the normal vector field, n of xy equals to partial x cross partial x, big X, partial y, what do we get? We get 1, 0, fx crossed with 0, 1, fy. This seems like a good job for not the determinant formula, the other way of thinking about things, right? This is x hat plus fx z hat crossed with y hat plus fy z hat, right? So I remember how I take cross products by hand, like x hat cross y hat is z hat, x hat cross z hat is minus y hat, fy. Z hat cross y hat is minus x hat, fx. And then finally the last term. So we have a binomial times a binomial. There are 4 possible products, but one of them 0 because z hat cross z hat is 0. And the others I just calculated. So what do you got? Going back to the other notation, lo and behold, minus fx minus fy, 1. What is that? Well, that's exactly the normal vector field that I erased before I wrote this example up. Because we had found previously that the gradient of something was equal to minus fx minus fy 1, right? And the gradient that I had there, of course, was z minus f of xy, right? Now let's, I got lucky. Okay? I got lucky. In the sense that these matched up exactly. In a given semester, if I played my cards differently, I might have gotten minus one of these as the other, right? So think about this. From the level surface perspective, I wrote down z equals minus f of, z minus f of xy equals to 0 is the level surface, right? Could I have written f of xy minus z equal to 0 as my equation? I could have, right? I could have multiplied it by 3, right? So since you're dealing with an equation, you can always multiply it by a minus or multiply even by a number, and that will influence your normal vector calculated from the gradient. So there's not there's an ambiguity there, right? There's a choice that has to be made. Which is the normal vector, up or down, right? And notice here, this is a subtle thing, but the order of the parameters matters. If I was instead saying the y was parameter first and the x was parameter was second, that would have reversed this cross product here, and that would have gotten a minus as well. So this is an issue we have to deal with. As we're talking about a surface, we're talking about the tangent plane, we're going to become invested in knowing which way's up. So like a surface is going to have an upside and a downside, right? There's going to be a side which is up. This is because what we're talking about is actually an oriented surface. An oriented surface is a surface which has a sense of direction, namely which way is up off the surface, right? And to define an oriented surface, how do you do it? You give me a set of points, and you give me a normal vector field. The normal vector field defines which way's up. All right? So these formulas are defining the tangent plane to be in the upward direction if we take z to be up, because the z component of it is positive. See that? So these would be the natural normal for like a tangent plane to a graph, because it has a normal which is upward pointing. So that's like the default orientation for a graph. But anyway, so I've showed you today how you can calculate tangent planes for level surface, for graph, and also for parametrization. And we'll actually calculate some more of these like Monday. But anyway, have a good weekend, you guys. I wish you all well on your Math 200 test.